Today we will focus on the topic of non-deterministic Turing machines. We will see that how non-deterministic Turing machine works and how we can convert a non-deterministic Turing machine, or rather how can we represent non-deterministic Turing machine using a deterministic Turing machine. Okay, so let us begin. Here you can see a non-deterministic Turing machine differs from the deterministic variety that we have been studying, having a transition function. So here, if you remember, in case of deterministic Turing machine, whatever the transition function we used, that delta q comma x, it was supposed to move to a new state, write a new symbol to that location, and we have to write the direction in which the Turing machine is going to move in the next go, right? Whether it will move left or it will move right. But in this case of non-deterministic Turing machine, the situation is like that, in case of any non-determinism machine, whether it may be finite automata, it may be, PDA, we cannot guess correctly that okay, for this input or for this state it is going to transit to this particular state only, right? So here same situation arises. So for a particular set of state and input, it may move to any number of states that is depicted by q1, q2, qk. It may write any symbol y1, y2, yk, or and for any of this new state and new symbol pair, the direction will be decided whether it will move right or left. That is denoted by d1, d2, dk here, right? So here this much of transitions are possible for a particular transition, right? So k is any finite integer. Now the language accepted by a non-deterministic Turing machine, that is M, is defined in the expected manner in analogy with the other non-deterministic devices such as NFA or NPDA. We have written PDA because we have proved that NPDA and PDA can work simultaneously, can give same kind of result, right? That's why we have written PDA here, right? So here we will see that how it process our input. We will be given with a string of input w, how it will process and how we are going to convert that using the deterministic Turing machine. So let us see here. Here we are going to prove that the non-deterministic Turing machine will accept no language that are not accepted by deterministic Turing machine. That means what? The language acceptance of deterministic Turing machine and the language acceptance of non-deterministic Turing machine should be equivalent. That we are going to prove here, right? L of whatever the Turing machine is, that is deterministic, will be equals to L of non-deterministic. That we will be proving here, right? So here the proof involves showing that for every non-deterministic Turing machine, we will denote it as m suffix n. We can construct a DTM, that is m suffix d, that explores the IDs that mn can reach by any sequence of its choices. Now it will be a bit difficult to understand now, but when we will move to the proof directly, we will see there will be a sketch, and from that sketch we can easily prove whatever we are now asking for, right? Whatever we are saying here, whatever the statement is, we are going to prove that, and there the concept will be totally clear. Fine. Now you can see that this MD, the deterministic Turing machine, will use a queue rather than a stack, so that after finite time MD has simulated all sequences up to k moves of mn. Now we will say why it is not using stack, why it is using a queue, right? So what is the necessity of queue is instead of stack? We will see in the proof that if you do not use any queue and you use a stack, the functionality will totally change. It is not possible to implement with a single stack, but it can be done in a single queue. Okay. So we are going to prove this one, that is, if Mn is a non-deterministic Turing machine, then there is a deterministic Turing machine Md such that L of Mn is equivalent to L of Md. That is we are going to prove. Okay, so see here what it is doing. Here the first step of MD, okay, MD, this is a deterministic Turing machine. First step, there you can see there are several IDs written, ID1, ID2, ID3, ID4, right? So it is the first step of MD. It is holding a sequence of IDs of Mn including the state of Mn, right? So what ID, what is the meaning of what ID consists of? We know ID consists of what? ID consists of a state and the input, whichever it is processing, and the transition, that is for this pair, where it is going to move, means which state it is going to move, which output it is going to generate, or which output it is going to replace, or rather which input symbol which it is going to replace in the place of the existing one, and whatever the direction is, whether it will move left or right, right? So this first step will consist of all the IDs of our non-deterministic Turing machine. Remember, we are going to simulate my non-deterministic Turing machine using a deterministic Turing machine, right? So we will take off whatever the non-deterministic Turing machine is doing, and we'll try to map it using a deterministic Turing machine. Fine. So first step will consist of all the IDs of non-deterministic Turing machine. Now the one of Mn is marked as a current ID whose successor IDs are in the process of being discovered, right? So here you can see that the marker is where you can see a small X is written just above the ID 3. So it is now processing the ID 3. So we know that our Turing machine always processes, means at least it starts processing from left hand side, means it will first process the first leftmost symbol, then next, then next, and then next. So you can easily say that whenever it is at ID 3, ID 4, ID 5, and so on is going to get processed, right? They are in the then they have not yet been visited if we just initiate the Turing machine, right? Now here the third ID is marked by an X along with an ID separator, which is star. So third ID, it is pointing to third ID, that's why it has been marked with a X. Now all the IDs to the left of the current one have been explored and can be ignored subsequently. So say actually it depends on since we are simulating it, we are not making the Turing machine function now, right? So since we have visited ID1 and ID2, so we can just discard them because we have copied them, we have simulated the functionalities of ID1 and ID2, right? Now we are processing ID3. So next ID4, next turn will be of ID4s, then ID5, and so on, right? Now let us directly move that to this one, that how it is going to process. So what MD will do depending on various situation it is going to face. First, MD examines the state and the scanned symbol of the current ID, that is here it is ID 3. Built into the finite control of MD is the knowledge of what choices of move Mn has for each state and symbol. So since it is storing the ID, that means it should have every knowledge, right? For this pair of state and this input symbol, what is the transition of a Turing machine, that is non-deterministic Turing machine, is doing, that will obviously written in ID 3, right? Now here, since it is copying or mimicking non-determinism, so here the chances will be ID 3 may consist of, means whatever the next state of ID 3 is, means say it is delta of q comma x equals to p comma y comma whatever L or R, whatever it is. So if p here is the accepting state, that means what? That means MD accepts and simulates Mn no further because it has reached the accepted state. So it do not require to simulate this non-deterministic Turing machine anymore. But this may not be the situation. If another situation arises, how we are going to proceed then? So if it is not accepting state and the state symbol combination has k moves, why k moves? Since it is a non-deterministic Turing machine, we know for a particular pair of state and input, there may be k number of moves, right? K is any finite number, but for the simplicity of assumption, we are assuming it as in the variable of k, it may have k number of moves. It can move to any number of states, right? So here it may have k number of moves. So in this situation, what MD will do? If you remember the conversion of non-deterministic finite automata to a deterministic finite automata, what we did, say Q0, for 0 input it is moving to Q1, for 0 input it is moving to Q2, for 1 input it is again moving to Q2, says this were the situation. So what we did, for each state and input pair, we just copied all the output several number of times, right? So that the total thing can be represented uniquely. Say we have copied Q1 twice, because for 0 symbol, say it is again moving to Q1, for 1 input symbol it is again moving to Q1. So we will make a copy of Q1, one for 0 transition we will use, another for 1 transition we will use. Similar thing will happen here. Then what if this kind of situation occurs that it has k moves, then MD will use its second tape. See, just it is marked with another arrow. It will use its second tape to copy the ID and then make k copies of that ID at the end of the sequence of IDs of the tape. So it is going to copy it k number of times. Why? Because it has k moves. That's why we need k copies of it, so that we can mark each and everything uniquely, since we are going to convert it to a deterministic Turing machine. Fine. Now MD modifies each of these k IDs according to a different one of the k choices of the move that Mn has from its current ID. So from current ID, what Mn was doing, we have this in our memory. So what we will do, we will just modify each of the k IDs. Means we will just map, okay fine, from this state, for this input it had this ID, for this one it had this ID, and so on. So we can just modify it according to our need. Fine. Now if this is done, MD returns to the marked current ID. What is the marked current ID here? That is ID 3. Erases the mark and moves the mark to the next ID to the right, because it needs to process the next. ID 3 is done. It has taken all the whatever the transitions ID 3 is doing for Mn. If it is an accepting state, fine. If it is not, if it is having k moves, it has copied it and has modified it separately, so that we can think of it as unique ID, right? Say ID 3.1, ID 3.2. In this fashion, it has arranged it as if it is a deterministic move. It has just separated it separately, and now the job of ID 3 is done. So we need to remove the marker from ID 3 and have to move to the next, that is ID 4. And again the same process will be repeated, right? It should be clear that the simulation is accurate in the sense that MD will accept if it finds that Mn can enter an accepting state, right? So obviously, so whenever whatever the accepting states of Mn is, or if it is having more than one accepting states, so MD will simulate accordingly. This should not be the situation that okay, these were the accepting states in case of Mn, we are using different states as accepting states in MD. That is not the correct one, right? So whatever the accepting states in Mn were, so that will be the accepted state of MD only. So however, we need to confirm that if Mn enters an accepting ID after a sequence of n of its own moves, then MD will eventually make the ID of the current ID and will accept, right? So we have to confirm that okay, that Mn has entered an accepting ID, and it may have n number of own moves. Means say so after from Q0 we have moved to Q1, then Q2, then again say Q0, then or say Q2, and then after that we have moved ultimately to the accepting state. So there may be n number of moves in between, so ultimately it has to go to the accepting state only, right? Now suppose that M is the maximum number of choices Mn has in any configuration. Okay, so say if this is a situation, say we are having 4 input symbols 0, 1, 2, 3. So from Q1, for zero input, say we can move to Q1, we can move to Q2, we can move to Q3, we can move to Q4, anywhere we can move, since it's a case of non-determinism. So if we are assuming that if m is the maximum number of choices that mn has, so what can be the total number of choices then? Now then there is one initial ID of mn, at most m IDs that mn can reach after one move, right? So if it has means it is having one initial ID, so what after one move, so if it has m number of choices, after one move, at how many places it can maximum move to? That is m. If it has means two moves, so again it is having more m number of choices, so m into m, that is m square. And if it has three moves, so it will be m cube. So in this fashion, if we means accumulate all n number of moves, it will be something like this. So for 0 moves it will be m to the power 0, that is 1. For one move it will have m number of choices, that is m. For two moves it will have m square. For n it will have m to the power n. So it is a series, nothing else, the 1 plus m square up to m to the power n IDs, right? So it is, it may at most it may have what, if we just it is a very simple thing, it's just summation of series, it will be n into m to the power n number of IDs, right? So now you can see, you will be able to know that why it is using a queue and not a stack. You can see here it is just a breadth first approach, right? So for one ID it is just exploring whatever there is in that level, then coming to the another ID, you know, ID 4, then again it is moving just searching for whatever the choices ID 4 is having. So in this fashion it is moving, right? Okay, so here in particular MD will make current and consider the successors of all IDs reachable by up to n moves before considering any IDs that are only reachable by more than n moves, right? So up to n moves, what are the different kinds of different IDs it needs to process? After n moves, what are the IDs it is still remaining it needs to process, that will be explored, right? Now as a consequence, the accepting ID of mn will be considered by MD among the first n m to the power n IDs that it considers, right? So if this is the total number of IDs possible for m moves, for maximum number of moves that MD is going to consider, right? For first n moves it is going to consider. Now here just we only care that MD considers this ID in some finite time. Obviously it should be done in finite time, we have to minimize in that fashion, right? And this bound is sufficient to assume us that the accepting ID is considered eventually. So thus what is happening, if mn accepts, then MD is also accepting. Whatever the language mn is accepting after say any number of moves, that we can simulate using MD only, right? So whatever language mn is accepting, MD is also accepting the same language. So we can conclude that language acceptance by the non-deterministic Turing machine is equivalent to deterministic Turing machine, whatever the language it can accept. Fine. So this is a very important proof. You may go through the slides again. I hope it will be clearer to you more. Okay. So in the next class we are going to learn this one, that is what is recursively enumerable languages, and we will see some exceptions there, that there will be some languages which will not cover under recursively enumerable language. Still Turing machine will be able to accept those languages. So what those languages are called. So we will see all this thing in our next class. This much for today. Thank you.